Welcome, Algebra 1 students, to Unit 1.5, Graphing and the Coordinate Plane. You are hearing the voice of Mr. May, and I will be your guide through this particular unit. As always, please make sure that you have your guided notes. We will be completing them as we proceed through the lesson. Make sure to use that pause button and the rewind button to ensure that you correctly complete your guided notes and that you fully understand the lesson. So without further ado, let's begin with our learning targets. Our learning targets, we have 3 of them for this particular unit. Learning target number 1.5a. I can recognize the parts of a coordinate plane. So what we will be doing by recognizing, you will be able to label them. You will be able to understand exactly the role that each of the parts of the coordinate plane will play as you begin graphing data in the future. Learning target number 1.5b, I can represent data on 2 quantitative variables on a scatter plot. So representing data, that is going to be, first of all, collecting data. And then once you collect that data, can you plot them on a coordinate plane in such a way that it is easy to analyze and draw conclusions? Learning target number 1.5c, I can interpret differences in shape, center, and spread of data sets, accounting for possible effects of extreme data points, also known as outliers. So this particular learning target ties in closely with 1.5b, representing data so that you can easily analyze and interpret, or along these same lines and thought. And specifically with 1.5c, we're going to interpret for differences in shape, center, and spread of the data. So let's consider what we have in front of us. We have what is called a coordinate plane. You may have seen it in the past. I want to point out one thing initially. The number line that we have used in previous units. If I were to draw a number line and I were to have 0 in the middle, moving to the right, as we have already discussed, are the positive numbers. Moving to the left, the negative numbers. Put -3, -4, -5. And so what we have is the ability to plot, which we have already done, plot data on a standard number line. So this is our standard number line. Well, what we see on the standard number line is that it is one dimension, meaning that we have one number in our data set. So if I had, for example, I think we used the Coach DeBoard has calculated or collected the amount of home runs by the players on the softball team. And what we would do is we would put a dot, for example, above the number of home runs that a player may have hit. So 2 home runs, if there were 2 players that hit 2 home runs, we would put 2 dots. And if there was someone that hit 5 home runs, we would have 5 dots. But what I want you to see is that this is one dimensional. The standard number line is one dimensional, meaning that it goes in only one dimension. Compare that to the coordinate plane that we have in front of us here. And notice that we are no longer dealing with one dimension. If you look at this axis, and we call them the axes, this axis is our x-axis, the x-axis. And this x-axis corresponds to our standard number line. So if we were just to have a single data point, and with that single data, we could just plot on that x-axis. But however, we have now included a second dimension, a second data point, two quantitative data points that we are going to represent with data. And so when we look at that second data point, it moves in the second direction or second dimension. So our coordinate plane, and let's write this in green, is two-dimensional. It is a two-dimensional representation of the data. And so if our first dimension we represent with x, which is a variable, and you will come to learn a lot of different terminologies for that x variable. As a quick preview, we'll also be calling it output, our independent variable. You will see this and be using this throughout, this terminology throughout Algebra 1 and even Algebra 2 and beyond. And so with the vertical axis, the one that's running up and down, we have as the y-axis. So we have the x-axis and we have the y-axis. And the y-axis, similarly to the x-axis, you will learn has many different terminologies associated with it, such as the output. And I may have actually, I want to rewind here for a second. Here's your rewind button, and you may realize that I accidentally called the x-axis, I may have accidentally called it the output. That is not the output, that is the input. So I'm going to write that down just to verify that we know that is our input. The y-axis is our output. So if you want, you can rewind and see if I accidentally misspoke. I'm relatively confident that I did. So our x-axis will also be called our input. Our y-axis will be called our output. Now, sometimes I see that students have difficulty remembering which is the x-axis, which is the y-axis. And so think about shaking your head yes. Somebody asks you a question, you shake your head yes. Which way? Go ahead and do that. Yes. If you're sitting by yourself, it may look funny, but that's okay. Shake your head yes. Which way is it moving? Up and down, vertically. Notice that it is going in the same direction as the y-axis. What letter does the word yes begin with? A Y. That is how you can remember it. If we use these little tricks, it helps us to make connections to some of the math terminologies that we are learning. So we know our y-axis. So when we are working through these coordinate planes, remember we're now working with two variables or two dimensions. So we're going to end up with two variables, two dimensions with two variables, unlike the standard number line, which was one dimension with one variable. We have a y-axis, which is the vertical direction, and we have the x-axis, which is the horizontal. So let's learn a little bit more about the specific parts of this coordinate plane. So definitions. We have a coordinate plane. Two numbers, or two number lines, again, we've already talked about our standard number line, that intersect at right angles. Well, the reference to a right angle is actually right here, and we can denote that by the geometry is actually what I'm using here. We can denote that right angle with that symbol, but I'm going to leave that off. I just want you to know that's where the right angle is. And so in the center where the two number lines intersect, that is what we call the origin. And I'm going to use this pink. That is where what we call the origin. So there's the origin of the coordinate plane. That is where our x coordinate is 0 and our y coordinate is 0. So notice that I have to represent both the x and the y. And so actually, let me go ahead and color coordinate these. Let's make our x red, and okay, so we have our x and our y. And when we represent the origin, that is a 0 x value and a 0 y value. That is the origin. Also included on the coordinate plane, we reference quadrants. And so our quadrants, we have 4 of them. And we have quadrants 1, 2, 3, and 4. And they divide the coordinate plane into 4 sections. So we've divided the coordinate plane into 4 sections. And the difficulty that I see sometimes is, how do I remember which one is 1, which one's 2, which direction does it run? Well, the easiest way that I've found to remember this is think about the direction that these are running. If I start at quadrant 1 and I go to quadrant 2, and then quadrant 3 and end at quadrant 4. What letter did I just make? And you may recognize that as the letter C. Well, interestingly enough, the coordinate plane begins with the letter C. And so if you can remember, the coordinate begins with C, and when you're looking at a coordinate plane, draw the letter C in the coordinate plane. The direction that you draw it is how you can remember how to number the quadrants. So now we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. The last bit of information that I want to point out is, notice that we have positive and negative signs in these quadrants. So if you look in quadrant 1, what we have is a plus. What that is telling us is that the x value, look back over here, the x value will be a positive number in quadrant 1. And so in quadrant 1, the y value will also be positive. Moving to quadrant 2, the x value in this case will be a negative number, so like a -4, -5, -7, -10. However, the y value will remain positive. So everything above the x-axis, again, my x-axis runs horizontally. Everything above the x-axis will be a positive y value. And so if I were to go to the third quadrant, we now have a negative x and a negative y value. And then we have in the fourth quadrant a positive x and a negative y value. And so what I could be able to do is give you a coordinate, for example, of -5. And so that is my x value. Remember, the x value is the first number in the coordinate. And if I were to give you a y value of -3, you should be able to tell me that I have a negative number and a negative number, meaning that this coordinate, this point, would fall into quadrant 3. So that is how we can determine where a point will fall in the coordinate plane and which quadrant we can find it. So the parts of the coordinate plane, we've already discussed some of these. Won't spend as much time. We've already talked about the origin. It's where the point where the two lines, the two standard number lines, intersect. And once again, we have our x value would be a 0 and our y value would be a 0. We've labeled the x-axis being the horizontal axis and the y-axis being the vertical. Remember, think about I'll put a little note here as a reminder. Shaking head yes. That's going to remind you that that is the vertical, the axis that runs up and down. An ordered pair. We've actually kind of talked about an ordered pair, although until this point, we have not identified it with specific terminology. An ordered pair is an x-coordinate and a y-coordinate. So it's a set of an x and a y that identify the location of a point. So an ordered pair. Think about it. How many are in a pair? Well, a pair is two of something. Okay? If I have a pair of socks, I have two socks. And so when I represent a pair in an ordered pair, I have to have two numbers. I have to have an x and I have to have a y. And we represent them inside parentheses separated by a comma. So for example, an x-coordinate may be 3, comma, 2 for the y-coordinate. And together, these two numbers represent a coordinate or a point or an ordered pair on the coordinate plane that can be graphed. And one other thing, when we are graphing, we have the x is graphed. Let's see. I'm going to reword that. The x direction is used first, then the y direction is used second, meaning you would move, in this instance of this coordinate, you would move to the right, or you would go to the 3 first on the x-axis, then up 2 on the y. So you would go in the x direction first and then the y direction. So changing gears just a little bit, not a lot, because each of these graphs could probably technically be represented with coordinate planes. They're just sections of the coordinate plane. However, they do have specific names. And in this case, we have a bar graph. And so a bar graph is used to compare amounts. And that's the important concept that we need to remember. It's used to compare amounts. So if I have a set of categories, in this case we have the categories of months. So in the categories of months, and I want to compare how much precipitation more than likely in Orlando will be something like rain. And so I want to compare how much rain between January or February, March, April, May. And so what we would do is on the horizontal axis, which is our x-axis, on the x-axis, we would list the categories. So our categories in this case would be our months, okay? And then on the vertical axis, these are the amounts. So amount of rainfall, we're going to say, because it's precipitation. So the amount of rainfall. And what this is going to allow me to do is to quickly determine specific points of information from the graph. So if I were to ask you which month had the greatest amount of rainfall, you could quickly look at a bar graph and say, oh, that was June. That's relatively, straightforward. I can find that pretty quickly. June has the most. It's the highest amount. If I were to ask which month had the least amount of rainfall, you may have already located the fact that April had the least amount of rainfall. So what a bar graph allows us to do is quickly make comparisons between categories of information. A histogram. A histogram is very similar to a bar graph. And so what we are looking at in this case is more of a frequency or a number of times and less about categories. And so in this case, what our comparisons are is the sample mean, and you may have already learned about mean, but the average versus the frequency. And so we use our x-axis and our y-axis to display what we are displaying as far as our number of times and our frequency. And what this also allows you to do, similarly to a bar graph, is make comparisons. So very similar to a bar graph without these specific categories like months or car colors or student height, something that would be more distinctive within a category. So if you have very distinct categories, you're probably going to look at a bar graph. Less distinct categories, you're going to be looking at a histogram, but it's plotted in very much the same way, with a bar extending up the y-axis, displaying the number of times that the data item has occurred. A line graph. A line graph is used to display the change in a data set over time, and this is where we have to make a very specific distinction between a bar graph and a histogram and a line graph. Bar graphs and histograms do not take into consideration time. Line graphs deal with time. So if you have a data set that has time involved, you really want to consider using a line graph. And so what this is actually a line graph of the Dow Jones Industrial Average. Now, the Dow Jones Industrial Average represents the stock market. The stock market over time from, you can see that the first year that we have is 1915, and the last year that we have is 1942. This is an actual graph of this time period beginning from 1915 to 1942, representing the value. So we have the value on this y-axis, the value of the Dow Jones Industrial Average and over time. And during this time period, this includes the Great Depression. And so this shows that during the time frame between 1929 and 1932, the Dow Jones Industrial Average lost value from above 350 to about 40 from 1929 to 1932. So what we can see is the change in value of the data over time. And we can even highlight specific intervals of time within this graph. But more importantly, we can see the changing of the data. So it goes up and down. We have a big spike in 1929, followed by a major drop during the Depression, and again, change over time. Circle graphs. Circle graphs are an efficient way to present data such as percentages or fractions of a whole. Now, with a circle graph, what we have to realize is that the total equals 100 or 100%, and that each one of these sections represents a part of that 100%. So if we were to add 65, 18, 10, 3, 2, and 2, the total should be 100%. And so if I want to represent what percentage or what part of the total a specific section or category of data would fall within a total, then a circle graph, or sometimes called a pie graph, would be an appropriate and efficient use. And so this particular circle graph represents the elements in the human body. So if I were to ask you what percentage of the human body is composed of oxygen, you could quickly look at oxygen, see that it is the purple color, and that purple color is this part of the graph, and it is 65%. So oxygen composes 65% of the human body. Now, one other thing that I want to point out, because this will come into an important role in a future lesson, is that in a perfect circle graph or pie graph, of the 100% of the area of the circle, this graph has been shaded 65%, or the oxygen portion makes up 65% of the circle. And so maybe to make this in a little bit simpler fashion with my nice circle here, if I were to say that something is 50% of the total, what I would do is I would divide the circle in half, and I would shade half of the circle, half of the total area of the circle. And so each one of these sections is shaded in the percentage that it is represented by that amount of element, the amount of that element in the human body. Let's do another one. What percentage of the body is nitrogen? Well, nitrogen is here. It is the red, so red shows that it is 3%. Now we could even see what combinations of elements are. So if I say, what is the total composition of the body of both oxygen and nitrogen? Well, we know that and is going to be an addition, so oxygen and nitrogen would be a total of 68%, and all I'm doing is adding the two. If I were to ask you what is the total percentage of both hydrogen and calcium, so I can look at hydrogen, which is the green, so that's going to be this, 10%. So we have 10%. And calcium is the blue, so that's 2%. So 10 plus 2, so 10 plus 2 is 12%. So 12% of the body is composed of hydrogen and calcium. So again, circle graphs are efficient ways for percentages and fractions of a whole. Box and whisker plots. Box and whisker plots summarize the distribution measurement of the data. So when we talk about distribution, it's kind of, how is the data spread out? What's the range? What's the middle? What are the highest values? What are the lowest values? And so what this highlights is we can quickly see where's the highest value. Well, the highest value is going to be at this end of the box and whisker plot. Specifically, the highest value is going to be this data plot. Well, what's the lowest value? The lowest value is going to be found to the left, and our lowest value will be this data plot. Where's the middle? Well, the middle is going to be exactly where you think it might be. It's going to be in the middle. And then we can also now determine the range of the data. We can see, what's the difference between the largest and smallest value. So we can make quick and easy conclusions about the data and how it's distributed. Scatter plots. Scatter plots are going to be a major focus in Algebra 1 because it allows us to show relationships in data pairs. So if we have two sets of data, we can analyze their relationship between each other. Does one affect the other? Are they independent of each other? Is one dependent upon the other? Are they correlated? So now we can analyze relationships, which then could give us a lot of power to model situations and even predict outcomes depending upon how the relationships interact with each other. Now, within a scatter plot, we have two variables. Again, we have two variables. We have our independent variable, and our independent variable is plotted on the x-axis. The independent variable is what is changed or controlled. We can change it, we can control it. As a scientist, for example, you'll see scatter plots and independent and dependent variables, for example, a lot in science class. If you're a scientist, if you're doing an experiment, you get to determine the value of the independent variable. You get to change it. You get to control it. So you're going to manipulate it to see how it affects the dependent variable. And the dependent variable is plotted on the y-axis. So we're going to plot the dependent variable on the y-axis, and that is what we are testing or measuring. So we're going to change the value of the independent variable, our x variable, okay, our input, to see how it changes or affects the dependent variable or our y variable or our output. Once we do that, we're going to get a set of coordinate pairs or ordered pairs. Okay, we'll have an x value, which is our input. We're going to perform an experiment with our x value, and we're going to get a resulting y value. And then we can take that. So, for example, we may end up with an x value of, let's use green here because it matches that. We may end up with an x value of 1, and when we have an x value of 1, we may see that that results in a y value of 5. Well, here is my independent and dependent variable. As we learned earlier about coordinate planes, we can graph this as an x and a y plot. And so that's what these x's are representing, are the plots of a sample data set. And once we plot that, we can then start to see if there is a relationship as we change the x value. How does the y value change? And we call that correlation. It is a description, once again, a description of the relationship. So correlation describes the relationship. If we have a positive correlation is an instance where the data sets both increase. So as the x value gets larger, the y value will also get larger. And in this case, what we have in this particular example that's on this coordinate plane is, notice that as the x values increase, and let me change colors to green here, x increases in this direction. Well, what happens as the x value increases? Well, we know that the y value, y increases as we move up. Well, what direction? As x is increasing, as we plot more values moving to the right, which direction is the y moving? Well, the y's are moving upward as well. So in general, the graph is moving in that direction. It is increasing. So we can say that this particular graph has a positive correlation. They're both increasing, the x and the y. On the other hand, if we have negative correlation, what you would see is that as one value increases, the other variable decreases. And most times what you see is that as x increases, as we move to the right, okay, as x increases to the right, I'm going to redraw a sample set of data. What we would see with negative correlation is that x moves to the right, the y value decreases. So in this case, we're moving downward. And if we have a data set that's moving downward, then we have negative correlation. And so negative correlation, we have one increases and the other data set decreases. So that is negative correlation. And then our last example, zero correlation, means that there is no relationship whatsoever. And I compare this to a graph that would, or a scatter plot that looks like chicken pox. So if I were to just have data that's all over, can't make any sense, pattern, conclusions, there is no seemingly apparent relationship between the x and the y values. This is what we call zero correlation. There is no correlation between the two. There doesn't appear to be any rhyme or reason to why a coordinate is placed where it is. And there doesn't seem to be an effect on the y value based on the x value. So this is zero. So once again, we have positive correlation where the data set will be moving upward. We have negative correlation where the data set will be moving downward. And we have zero correlation where it just looks like there is chickenpox. Again, think chickenpox. There is no apparent relationship between the data. Looking at example 1, highlighting learning target number 1.5a. So what we want to do is label the coordinate plane, then plot and state the quadrant where each coordinate pair will be located. So go ahead, hit pause, see if you can work through each of these examples, and when you're finished, hit play again and we'll work through them together. So now that you have worked through it together, let's begin by labeling the coordinate plane. And so the first thing that we need to label are the axes. So the x-axis, as you recall, is the horizontal axis. And then the y-axis is the vertical axis. And we always use the bold, heavy lines that usually run through the middle as our axes. We also could label the origin. So we could have that as our origin. And we may recall that 0, 0 is the origin. And then if we were to label our quadrants, can't remember which direction they go, what is the first letter in coordinate? It is a C. And so we begin in this, draw a C. And that tells us that our quadrants are quadrant, use a different color. We have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, so we have now labeled our coordinate plane with our quadrants. So now we need to plot our points. And remember, this is our x point is always the first one in the ordered pair. And the y is the second number in the ordered pair. And we always plot the y first. So beginning at the origin, or the x first, I'm sorry, we always plot the x first. So beginning at the origin, we move to the right by 4 because numbers increase moving to the right. So 1, 2, 3, 4. Then we move the y direction. In this case, we're going to move down. And so this will be our plot of 4, -3. And we can see that we are now in the 4th quadrant. And a way that we can remember that, if we just want to look at the number, is the 4th quadrant is a positive x value and a negative y value. So we have a positive and a negative. Let's plot our next coordinate. So we have -2, so we're going to move to the left 2. And then we're going to move down 5. 1, 2, 3, 4, 5. And so we have our next coordinate of -2, -5. And so we can see that we have found ourselves in quadrant 3. And as a reminder, quadrant 3 is a negative x and a negative y. Negative x, negative y. And let's put that back in. Okay, C. So our coordinate is 1, 7. So we will move to the right 1 because we're always going to move to the x direction first, and then we have to move up 7. 1, 2, 3, 4, 5, 6, 7. Let me double check. 1, 2, 3, 4, 5, 6, 7. Okay. So our coordinate is 1, 7. We find ourselves in the 1st quadrant. And to have a quick system of being able to look at it, we know that this is going to be a positive x value and a positive y value. Our last coordinate, -3. Moving to the left on the x3, -3. Up 4, 1, 2, 3, 4. We have a coordinate of -3, 4. We have found ourselves in the 2nd quadrant. That is a negative x value followed by a positive y value. And so we have successfully labeled our coordinate plane. We have plotted the ordered pairs, and we have located the quadrant in which they fall. Example number 2, highlighting learning targets number 1.5b and 1.5c. It asks to represent the data or the table of 2 quantitative data plots. So we have 2 quantitative data plots, one being the minutes of studying, the other being the exam score. So we're going to represent these 2 data plots on a coordinate plane and then interpret the shape, center, and spread, accounting for possible effects of extreme data points or outliers. So what we need to do, first of all, is we need to determine which is the x or input or independent variable and which is going to be our dependent. Well, to begin, which one can we control? Well, we can really control our minutes of studying. So this is going to be our independent variable. So this is our independent variable, which we represent with x. Now, logically, if you think the minutes that we spend studying will affect our exam score. So you would think the more you study, more than likely, the better exam score that you would get. And so our minutes of studying would affect our exam score. So what I want to do, I just noticed, I want to color coordinate these a little differently. I'm going to write this one. This is our independent variable, which we represent with an x. And this is the dependent because our exam score will depend on how much we study, and we represent our dependent variable with a y. So now you may recognize that we have an ordered pair. So our ordered pairs that we can now write are going to be 0 for our minutes of studying. And what score would you have estimate that you would get if you studied 0? Well, you would estimate that you would get a 40%. If we were to look at if we studied 15 minutes, our estimated score would be 55. If we were to study for 30 minutes, our estimated score would be a 70%. If we were to study for 45 minutes, our estimated score would be an 85%. And then lastly, if we were to study for a full 60 minutes or 1 hour, we would estimate that our exam score would be a 100%. Now you may recognize these as ordered pairs, but these ordered pairs are showing the relationship, again, a relationship between the minutes studying and an exam score. And as you might recall, we represent or best represent data that shows relationships on a scatter plot. So the most appropriate type of graph would be a scatter plot. So let's plot these on a coordinate plane as these ordered pairs as a scatter plot on a coordinate plane. So looking at a coordinate plane, we have our origin. Now one thing that we have to realize is that these points are a little larger than 0, 1, 2, 3, 4, 5. So we're going to have to change our scale, and that's okay. So our scale is going to be by 15. So we have 15, 30, 45, and 60. Actually, let's look. Is that, let me double check. So 0 minutes of studying and 15, that is correct. Okay, so our x-axis, again, is our independent variable. And so we are going to have, I'm going to write it this way. It's a little bit easier to see. So 15, 30, 45, and 60. Those are our minutes of studying. And better yet, I'm going to color coordinate them in green so that it is 15, 30, 45, and 60. And if we look at our exam scores begin at 40 and go to 100. So I have to have a relatively large range, and I've got, so if I go by tens, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, that'll work. So I can have a 10, 20, and I'm going to have to write it a little smaller, I believe. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So now I'm going to plot these points. So if I studied for 0 minutes, I would get a 40. Well, where is 0? Well, 0 starts at the origin. I don't go anywhere on the x-axis, and I would only get a 40%. So there is 0, 40. If I study for 15 minutes, I estimate that I would get a score of 55. So I'll go to the 15, and then I go up to 50, and it's halfway between the 50 and the 60, so it would be 55. If I study for 30 minutes, I estimate that I would get a 70, so go over to the 30 and then up to the 70. When I look at the 45, I would estimate that I would get an 85, so that would be here. And then lastly, if I were to study for 60 minutes or a full hour, I estimate that I would score a 100%. So I've plotted the data and I've represented the relationship between the two quantities, but I have yet to distinguish them by or interpret them based on shape, center, and spread. Well, when I talk about shape, center, and spread, what I'm referring to is the correlation. And so when I look at this, I notice, okay, first of all, are they correlated? Well, it looks like they are. It doesn't look like chickenpox. So it does look like the data is correlated. And so it looks like that there is a correlation. In what direction is this actually moving? Well, it's moving in the upward direction. And so I can remember that data that moves in the upward direction is positive. So we have a positive correlation. Okay, so we have shape, center, and spread. And so we know that the shape is a positive with a correlation. And so now we have to think about the spread. And the spread is referring to outliers. Are there any outliers? Now, what an outlier is a data point that doesn't really match the rest of the set. And an analogy or an example could be if I were to choose 5 random students from the class and we were to go on the basketball court and form a basketball team. They would have an average skill level of basketball. And we could plot their skill levels and they would be relatively close, not too far apart. But then if I were to invite LeBron James to come in and join our team, and then I were to plot his skill level, what do you think might happen? Well, it would completely skew the data. It would throw the data entirely out of balance because his skill level is so much beyond any other players on the team and probably within the school that it wouldn't really match the rest of the data. He would be considered an outlier, not a real representative of the data that we are actually representing. And so what we need to look at, is there anything that is not within this data set that would be considered an outlier? Is there anything in that data set? And so what that might look like on a graph is if I had a data point that was maybe way over down here somewhere. Doesn't really match. It doesn't go with the rest of the data. Or if I were to have a data point that was somewhere down here. These data points do not represent the rest of the data in the same manner. So we would call those outliers. However, in this case, we can notice that all of this data is relatively tight in spread. There is not a lot of variation in it. And we know that it's positively correlated and they relatively are uniform as far as how they are in relation to each other. So in this case, we would conclude that there are no outliers. So there are no outliers in this case. So we have positively correlated data with no outliers. And what this tells us, if we were to come to a conclusion and interpret this, what this would tell us is that as we increase hours of study, there is an increase in exam scores. And so that is our interpretation based on center, shape, and spread, representing the data, again, best on a scatter plot because we are wanting to highlight the relationship between the two data points or two quantitative data sets. And so this concludes our lesson on Unit 1.5, Graphing and the Coordinate Plane. Please make sure that you go back and review your guided notes. Make sure that you rework the examples. Make sure that you have a full understanding of the content. And if you do have further questions, please ask one of the math teachers. We are more than happy to help you with any questions that you might have. And as always, have a great day, and we look forward to seeing you in class.